Okay, well, first I'd like to thank the organizers for organizing this meeting and the audience for staying so long into the conference, and also for covering a lot of the topics I would normally have in my introduction, which will save me time. So yeah, I'm going to be continuing this theme of collisionless plasmas and focusing on our expectations for energization of plasmas by turbulence and collisionless accretion disks, but I'll be doing it from a local perspective, not really a global perspective. Okay. So yeah, so what's the motivation for this? Well, as we heard in previous talks, in systems such as hot accretion flows, we expect them to actually be collisionless plasmas, and thus we expect non-thermal effects to develop in the plasmas, leading to many kinetic phenomena that require the Vlasov of Maxwell equations, as shown in the previous talk, rather than they can't be described by MHD fluid models. So for accretion flows, there are several different types of observational consequences we want to understand, and we want to understand what plasma process is responsible for it. For example, we want to understand broadband radiation spectra, and this requires non-thermal electrons to be spanning a broad range of energies, implying a non-thermal particle acceleration mechanism, as discussed in the previous talk in a different context. We also want to explain why do these systems have relatively low luminosity compared to naive predictions based on energetics. And this has been attributed to the plasma being in a two-temperature state where the ions are much hotter than the electrons. And this connects to the electron-ion heating problem that Greg Howes discussed yesterday. Finally, we also want to understand what is the source of flares in X-ray and near-infrared wavelengths, and it's observed that these are intermittent flares, and so we need some sort of localized mechanism, possibly a beaming, to explain those flares. So those are the motivations to have in mind, and I'll be touching on all of them to some extent here. So of course we know turbulence we know accretion disks are extremely turbulent. I think this is beyond debate for this community. So this is very nicely demonstrated by general relativistic simulations like the ones I shown here by my collaborator Barker Perda. And so at the MHD level, we know that the turbulence could influence the dynamics of the accretion by controlling the magnetic fields and the accretion process, angular momentum transport. But the turbulence is also a dissipative process, and so if we want to understand the heating of the plasma, particle acceleration, and radiation emission, we need to understand the turbulence. And specifically, this is outside of the MHD modeling, so we need to know the collisionless aspects here. This nice spectrum of the solar wind came up many times yesterday. I like it a lot. So we expect the turbulence to maybe look something like this, but with a much longer inertial range, because it's not limited to just 3 orders of magnitude like the solar wind. But qualitatively, it would be something similar. But one other difference from this solar wind is that in these accretion flows, the plasmas are generally in a relativistic regime or a trans-relativistic regime. And this could be encapsulated by this parameter sigma, which is the magnetic energy relative to the energy in the particles of the plasma to an order unity factor. When this is comparable to unity or larger, means that alpha in velocity could be close to the speed of light, and it's relativistic in that sense. And the plasma quickly heats up the particles to relativistic energies. So that's the regime we're interested in. And this is in more detail what the turbulence looks like in these systems. This is going to be showing the same simulation that I showed on the previous slide. The density here is shown. So red is high density, blue is low density. And this is during a magnetically arrested state where magnetic flux builds up near the horizon of the black hole, and it regulates the accretion. So let's play through this, and we could see it is indeed very highly turbulent here, but it's a very messy type of turbulence. There are many instabilities present here. It's very inhomogeneous. There's large-scale structures. So what the main point of this talk is to try to understand this type of turbulence in the context of accretion disks, and whether we should expect any idealized turbulence models to hold there or not. So specifically, the type of instabilities that we see occurring here are magnetorotational instability, which would be occurring in the outer regions here, Rayleigh-Taylor instability on the interface between the cavity and the ambient flow. And there's also some Kelvin-Helmholtz instability, which I won't be talking to, but there's been nice work by Lorenzo Ceroti, for example, on that problem. So how does this compare to the pristine case? And one more thing to emphasize here is that this cavity, this would be a very high sigma parameter in here. So this would be a very relativistic type of turbulence within the cavity. And it would be electron-positron loaded, a pair plasma. But then this ambient flow would be in a trans-relativistic regime, where the electrons are ultra-relativistic, but ions are sub-relativistic. So that's important to keep in mind. These are the typical parameter regimes that we're in. So so first I'll talk some things about just pristine kinetic turbulence, by which I mean externally driven turbulence in this relativistic, trans-relativistic regime. Then I'll be talking about these two instabilities. So just to start, I'd like to acknowledge that by this point, as Luca mentioned in the previous talk, there's been a lot of work on kinetic turbulence, especially in the relativistic regime, and with many different setups, and they've been mainly focused on studying particle acceleration. So I've mostly focused on driven turbulence, either electromagnetically or by body force, and I'll be describing some results on those. There's also nice work on decaying turbulence by Luca and by alpha wave collisions, which are a controlled wave driving turbulence by Jonas Natla. So different drives could lead to different cascades, even at the MHD level, alphenic versus magnetosonic cascade, and so those could influence the dissipation. So we already had an introduction to kinetic simulations, but just to assure you, these look like turbulence. Here's a fly through one of the boxes. This is already 6 years old, but it's still, I think, a reasonably nice simulation. Current sheets form, you get all these turbulent density structures. It looks like a lot of turbulence. These PIC codes work well in this regime. And one of the main outcomes of this is that we indeed see particle acceleration. This is exactly what Luca was showing for the non-relativistic case in the previous slide, but here we're in the relativistic case where I'm going to be using a gamma factor to represent the particle energy. So we started with a thermal state, it becomes highly non-thermal. And some lucky particles, they're stochastically accelerated to very high energies through this process by interacting with the turbulent fluctuations. We find that the turbulent acceleration process could be described very well by Fokker-Planck equation in the energy space, or equivalently in the momentum space of the particles. And this diffusion coefficient at high energies is exactly what's predicted by second order Fermi acceleration to a factor of order unity. There are parts like the low energy diffusion coefficient and this non-zero advection coefficient, which we don't fully understand, and they're in fact essential for forming the power law in this domain. And this was a topic discussed by Martin a couple days ago. So he's expert to talk to on that topic. So once you include all of these Fokker-Planck terms, in our experience, it seems that the evolution of the particle distribution is very well reproduced. So one thing to emphasize beyond that work is that when you get to the trans-relativistic regime, the manner in which you drive the turbulence actually becomes important for whether or not you observe particle acceleration. And the simplest thing you could do is to compare solenoidal driving with compressive driving. Has often done in MHD simulations as well. With solenoidal driving, we end up getting a lot of shear flows in the turbulence. And these are 3D simulations, and it's just a fly-through. And you can see lots of shear flows in the simulation, but then with a compressively driven case, it's much different. You get these big compressive density structures. I'm just showing the electron distribution here, but ion distribution is pretty similar. For the electrons, in the incompressible case, we don't get any particle acceleration in this regime, whereas in the for the compressive case, we do see a power law forming. Is this surprising? I don't think so, because quasi-linear theories often predict that compressive cascades would be more efficient at accelerating particles, and this seems consistent with those expectations. So one other thing that the driving mechanism affects is the electron to ion heating ratio. So as Greg Howes discussed yesterday, it's a very important question for modeling emission for observatories like EHT. What is this ratio of electron to ion heating as a function of various plasma parameters? And there are various cascade models, non-relativistic simulations which have studied these problems, but they're not quite in this regime, and they ignore the electron physics. So we want to study this with the fully picked simulations, and we get a result which looks like this. This ratio tends to be less than 1 in the trans-relativistic regime, indicating that the ions are heated more than the electrons, which is exactly what the models need for the accretion flows, radiatively inefficient accretion flows. When the driving is compressive, then the ions are heated even more than when the driving is incompressible. And this is consistent with results in the gyrokinetic limit by Kawazura et al. So the bottom line here is it seems that the driving dependence is an important thing to take into account in modeling any sort of turbulent dissipation. We also have a nice little empirical formula here, which I won't go into, but feel free to look into the paper too, if you're interested in that topic. Okay, so now I've motivated that driving mechanism could be very important for the turbulent dissipation. So let's try to work toward driving turbulence in a more realistic way. So now let's come back to this Rayleigh-Taylor instability problem. So here's the same animation that I showed earlier, and I'm just going to play again what I mean. There's this cavity near the black hole. You see these fingers forming at the interface, and this is very clearly a Rayleigh-Taylor finger, which has been, studied for many years in the fluid context. But this is an unusual regime because we have a cavity which is very high magnetization. We have ambient flow which is trans-relativistic. We have to do it in the kinetic framework to understand the dissipation. So it's a completely new regime. Very interestingly, we think this potentially is a well-motivated problem because if these Rayleigh-Taylor plumes that form are able to dissipate into non-thermal energy, then they could explain perhaps near-infrared flares for Sagittarius A star, which have been observed for several years, or decade now. So that's one additional motivation. So let's look at how to do this. So we want to do PIC simulations of the Rayleigh-Taylor instability, and we want to do this locally. So we have a cold, dense slab on top of a hot cavity in some periodic box, quasi-periodic anyway. And there's a gravitational force which is pushing down, and that's what leads to the instability. An important thing to account for in this setup, if you want to bridge to reality, is that the magnetic field rotates between the two domains. And so we need to take into account the rotation of the magnetic field between a cold slab and a hot cavity. Here it's a pretty close to 90-degree rotation, but in general that angle could vary, so it's an important parameter. This is all so far for paraplasma and two-dimensional domain, just to understand the principles of the instability. And the way we orient the domain, there's going to be an out-of-plane magnetic field, but then there's also in plane magnetic field, which changes direction across the interface, and so that component is allowed to reconnect. And let me show you the dependence of the rotation angle. So this first one's going to show zero rotation of the magnetic field. So the magnetic field is purely outside of the domain in this case. And what happens is that everything just falls apart and you get a lot of mixing and a lot of chaos. But this isn't turbulence, it's just a lot of mixing. There's not really dissipation going on here. So that's one case. The other case I'm going to show in the center is orthogonal fields where there's a 90-degree rotation between the two domains. In this case, you actually could get reconnection at the interface, and this inhibits the mixing between the two domains, and so the mixing stalls, and it ends up just staying in a state which doesn't mix very much, and there's not much interesting dissipation going on either. In this last case, we have a 45-degree rotation, and here both reconnection and the Rayleigh-Taylor are able to grow, and so we get this apocalyptic plume which forms, and then it reconnects, and then you get a lot of turbulence in between the plumes. So that's just right if you want to get something interesting to happen. So the energy evolution for different components is here. You probably can't see what it is, but the main point is that all the energies are basically increasing exponentially as you expect for instability. Then there's also an inverse transfer of the turbulent energy from the initial small instability scale up to larger scales, and you eventually get something which looks like a turbulent power law, despite the fact that this is all organized at that large scale plume. So this looks very much like turbulence in this sense. Now let me show you what happens with the particles. So on the left, I'm going to be showing one of these simulations, and I'm going to be showing you tracked particles, which are these colored objects down here. And these get accelerated when they get stuck in that reconnection layer. And as you can see from the energy evolution on the right, when that reconnection event happens, that's when they're energized very strongly. And this is a very strange type of reconnection because it's forced in some sense. It's a very high magnetization inside the layer, low magnetization outside the layer. It's turbulent, even though it's 2D. And then lots is going on there. It's not really the normal Harris sheet type of reconnection. In the end, this is enough to give you efficient particle acceleration if you have a high enough density contrast between the ambient plasma and the cavity. And we did the calculations in the paper, and we think it's enough to explain the near-infrared flares. In the future, we're working on 3D and electron ion composition, which I think is what needs to be done to really put the nail in the coffin on this problem. So with the remaining 2 minutes, let me just mention some work that my collaborator has been doing, Fabio Bacchini, on the magnetorotational instability. So I think we already talked about MRI a little bit in this workshop, so I'll skip the motivation and just say that we did these PIC simulations of turbulence in a shearing box to study the development and saturation of the magnetorotational instability. Here's a quick animation of what it looks like. This is a problem which has been studied by several groups in the past, but these are bigger simulations. We used very large computers for them. And so we think they're a little bit more robust than what's been done in the past. Anyway, the turbulence reaches some saturated state. We have a nice turbulence spectrum in this saturation. And the main things to know about this turbulence is it's mostly incompressible, so it's solenoidally driven. It's somewhat subrelativistic. It has a beta which is about 10. and it has a magnetization which is much less than 1. And the expectation for these parameters is that they're not really favorable for turbulent particle acceleration based on what we know from the pristine simulations. But nevertheless, what we found in this work was that particle acceleration does happen, and fairly efficiently. And this seems to be an effect of the fact that you have a lot of free energy in the shear rather than in the magnetic field, and so you're still able to feed particle acceleration even though you wouldn't naively expect it just based on the magnetic energy. One other thing we did here was we added radiative cooling on the particles to see, to basically remove the effect of particle acceleration in the early stages of the simulation. And so when we have radiative cooling, it's in a quasi-thermal steady state. And when we turn off the radiative cooling, we get the particle acceleration. So there's no particle acceleration from the linear stage of the instability. In this case, it's all from developed turbulence, and we just turn off the acceleration if we have the radiative cooling, and then we get it when we turn off the radiative cooling. So that's where things stand on the MRI. The future direction there is to do electron ion plasmas. This is all for pair plasmas, so that's still needs to be studied. So with both of those problems, once we do the electron ion case, we will be studying the energy partition between electrons and ions, so that'll be an interesting direction to go into as well. So I'll just leave my conclusions up here, and thank you for your attention.
Okay, let's start with the questions. Yeah.
Yeah, so I want to ask you, in the case with solenoidal driving, you also have compressions of magnetic field, right? But
well, compressions, yeah, so even if you drive it solenoidally, it's kind of inevitable that you will get some compressibility out of it, yeah.
So you think, what is your insight in why the acceleration efficiency is different, depends on the driving?
Well, so we get, in the compressively driven case, there would presumably be more fast modes driven at the larger scales. And it's a little bit complicated to say what happens with them because they could damp at large scales through the Landau damping. And whether this damping process is favorable for particle acceleration or not is a little bit unclear. But I think the story is that there is some presence of fast modes which are either not damped or are damped at relatively large scales, and this influences the acceleration. In MHD, you would expect that because the cascade is isotropic for fast modes, that would be more favorable for particle acceleration. It's a little bit hard to tell in the collisionless case whether that cascade happens, because what we observe is mostly an incompressible cascade, indicating that the dissipation is happening at large scales for the fast modes.
Okay, thank you.
Axel?
Similar aspect, when you have this compressive driving, you, in the fluid description at least, can produce vorticity through 3 mechanisms. One of them is through shocks. In your case, you are collisionless, so that may not actually work, which is perhaps interesting. But then you still have baroclinic terms, which is probably not vanishing in your case. And then finally, magnetic fields, which is also not vanishing. So why are they inefficient in your case?
No, they certainly operate. And so it all comes down to what is this partition between the different modes that comes out. And when you drive incompressibly, it has a tendency to have more Alfvénic-like fluctuations, but it'll still have compressive fluctuations, and vice versa. So there's always a mixture, and I would say, there's tens of % of energy in each of the different modes. It's just that there's a bias depending on how you drive it. Yeah.
In 2015-8, Kadovaki, myself and Jean Stone, we published a paper where we studied MRI and Parker-Rayleigh-Taylor instability in the shear box simulation, a very high resolution. Of course, it's a MAGD fluid simulation, and we found out that reconnection driven by these two sources of turbulence is pretty, I mean, there are several events of reconnection, several layers, and in both effects, both instabilities actually are I mean, the Rayleigh-Taylor, the Parker-Rayleigh-Taylor instability does grow through the coronal region. And it's not, I mean, it doesn't kill turbulence. Actually, it helps to drive further turbulence. And we even saw the dynamo, the small scale dynamo process occurring thanks to the interplay between these two sources of these two instabilities, which are sources of turbulence. So I wonder how in the collisionless limit, why is that the Rayleigh-Taylor instability this not kills turbulence, actually does not allow for the development of the turbulence? And is that related to the fact that you have these fully relativistic electrons competing with the low energy or transrelativist protons, and the mass ratio between these two has to be assumed that as such in the collisionless calculation in such a way that you might have this dissipation or limitation with the Rayleigh-Taylor, the Parker-Rayleigh-Taylor instability. Can you comment on this?
Yeah, that's an interesting question. So I think probably that latter aspect, the composition, I don't think that's the main player that's limiting the interplay. I think, well, the main thing would be that this is two-dimensional. So with three-dimensional, I think turbulence would be more easily driven, and that would, of course, change some of the features.
This is 2D?
Yeah,
okay.
all the RTI was 2D. Yeah. And the other thing that could be done here, of course, is adding the shear, which you mentioned at first, I think. This doesn't have any shear, but it could also, to study this interplay between Kelvin-Helmholtz and Rayleigh-Taylor instability, if you add a shear, that could also have an effect of enhancing particle acceleration and turbulence, perhaps. Yeah.
Okay, I have a very quick question. Could you go to the slide on the MRI with the different stresses?
See the stresses, yes.
So the Reynolds stress kind of flips sign, periodic.
Well, it's a logarithmic scale, so I can't say for sure.
Okay.
It does look plausible that it does flip, but yeah, we'd have to look at the data for that.
Okay, I think we can finish a minute early if everyone just starts clapping.